Hello everyone, in this part we'll learn another DP for 0-1 knapsack problem when item profits are small. So let us recapitulate what is 0-1 knapsack problem. In 0-1 knapsack problem, we are given n items and A1 to AN. Each item AI has size SI and profit PI, and there is a knapsack of integral capacity B. Our goal is to find a subset of items such that their total size is at most the knapsack capacity B. It's called knapsack capacity constraint, and under this constraint, we want to maximize the profit. And in this problem, we're talking about 0-1 knapsack, where we can either select an item or we don't select an item. We cannot select multiple copies of a same item, or we cannot cut the item. In the last part, we talked about one dynamic program, and the runtime was order NB. It was a pseudo-polynomial time algorithm. And in this part, we'll talk about another pseudo-polynomial time algorithm, but now it is in terms of profits. So let's look at this dynamic program, where in the last part we saw an ordering based on the number of items and size, but now we do an ordering based on the items and profits. So let us say P is a maximum profit item. Among all items is the maximum profit item. So optimal solution value should be at most n times P. There are n items, and even if each item has same profit and equal to the maximum profit, that's the maximum value of opt. Now we're looking at a dual variant. So there are two variants of the problem. In one case, we have a fixed knapsack capacity and we're trying to maximize the profit. Other option is we fix the amount of profit and then we minimize the size of the knapsack where we can get the profit. So that variant will give us this, this definition that for all I equal to 1 to n and p from 1 to np, these are all possible profit values and all number of items, we define SIP to be a subset of items from A1 to AI whose total profit is equal to P and whose size is minimized. So that is the difference. Now we are looking at the total profit and trying to minimize the size. In the previous variant, we are trying to maximize the profit and we have a fixed size, an upper bound on the size. In this case, actually, we can also make sure the profit is greater than equal to P. That's also fine. But if we want to minimize the size, equal to P is better to have. And then we define AIP to be size of SIP. And if there is no such sets which has profit exactly equal to P and from items A1 to AI, then we define it to be infinity. Now let's look at the base case. So in this case, actually, we will use exactly equal to P, not greater than equal to, but exactly equal to P. So in the base case, we have AI0 equal to 0 for all I. That means that I'm just looking at profit 0 here. So we want a subset of items such that total profit is 0 and size is minimized. In that case, we can just take no item and that size is 0. So it's AI0 equal to 0. In the second, we are defining A1 profit A1 equal to size A1. If we have only 1 here, that means we are looking at subset of size. Only we are looking at subset of A1. So either we take the item A1 or we don't take. And then we want exactly profit P. And we have to minimize the total size. So if I take the item A1, in that case, the profit we get is profit of A1 or P1. And in that case, we have size of SY, size of A1. But for any other values, apart from profit of A1, we have it to be infinity. So let me just remove it. Just P. So for any other A1P, we define it to be infinity because that's not possible. We cannot achieve any other P except size of A1, except profit of A1 by taking only item 1, A1. So item 1 and A1 I'm using interchangeably. Now let's look at the recursion. There are two cases. In one case, we take the item I plus 1. In that case, we have already attained size S AI plus 1 from the item I plus 1. And then we are left with profit P minus profit of AI plus 1. And in this case, we are assuming profit of AI plus 1 is less than equal to P. Otherwise, we cannot put the item. So that's the edge case. If already profit of AI plus 1 is more than P, then we cannot take the item. So AI plus 1 P is AIP. And in the other case, if we don't take the item, then also it's AIP. So that's the recurrence. So spend maybe a couple of minutes to understand this recurrence and the relationship and why this is correct. If we solve this, why are we getting a correct solution? And then we can check the optimal substructure property as a homework. We have done it multiple times now. And then finally, we return this solution. We look at all A and P such that it's less than or equal to B. That means we're looking for all profit P which can be attained from subset of items from 1 to n, and total profit is total size is at most B. And among them, you find the maximum profit. Whatever that value, that is telling us that is the maximum profit you can get for knapsack capacity B. That's the solution we return. So what's the runtime here? This, if we write down the same way like last time, iterative way, then there are a number of, it's a two-dimensional table again, and this I can take n possible values and profits can take np possible values, total n square p time it can run. So if p is small, which is maximum profit item is small, let's say in polynomial in n, then actually it's a polynomial time algorithm. In general, it's a pseudo polynomial time algorithm, but when the profits are small, then this particular DP is very useful. In fact, we'll see another advantage of this DP, that this will lead to a very good approximation algorithm for the problem. And this knapsack problem is very well studied for last 20, 30, 50 years almost. From 70s, it has been studied. And now we have a kind of a good understanding about the problem. In fact, it was almost resolved recently in this couple of stock papers, which showed that you can solve knapsack with runtime this. So O tilde of n plus s max square or O tilde of n plus p max square. So let me define what I mean. So nb is the first algorithm that we saw last time. And now we saw n square p max, where p max is the maximum profit item. So nb you can also write it as n square s max, where there are s max is the maximum size of an item and there are n items. Now, from n square s max and n square p max, the multiplicative factor, we have achieved now n plus s max square and n plus p max square. So this n is not multiplicative now, it's separated here. And there is also proof that there is a conjecture called mean plus convolution conjecture from fine grained complexity. And that shows that this is kind of the best you can do. That you cannot achieve better than order of n plus s max to the power 2 minus delta approximation algorithm. So the square is really the bottleneck. And this tilde means that we are hiding some terms which are log of this. So let's say log n, or log s max, or log p max, or some power of that. So we'll say polylog factor. So n to the power, let's say 1000, and s max to the power 10. This is polynomial in n and s max. And now we take log of this. So maybe log n times log n to the power 2 and log of s max to the power 3. That is polylog factor in this. So this polylog factor we're writing here with O tilde notation. So this ends the algorithm for knapsack. But now we'll see how to use this previous dynamic programming based pseudo polynomial time algorithm to get a very good approximation algorithm called FPTAS, or fully polynomial time approximation scheme, in the next one. Thank you.